In this video, we will take a look at acid-base properties of salt solutions. Now, recall that when we react an acid with a base, it can generate a salt. So salts are the product of neutralization reactions. Now, when we talk about neutralization, neutralization is in reference to the reaction. It's an indication that all of our acid has reacted with all of our base. It's not necessarily connected to pH. We could do a neutralization reaction and we could end up with a pH other than 7. This is because, remember that when we're reacting an acid with a base, each acid and base have conjugate acids and bases. That's what's forming our salt. So our salt is the result of the conjugate acid and the conjugate base. And those conjugates can have acid-base properties. And these properties are going to depend on the strength of the acid and base that are forming that salt. So remember in our discussion of acids and bases, the stronger our acid is, the weaker its conjugate base will be. That's what leads it to be a strong acid and stay dissociated. The weaker our acid, the stronger its conjugate base will be. And the same is true for bases. So the stronger the base, the weaker the conjugate acid. So with that in mind, when we talk about salt solutions, we can have a neutral salt, an acidic salt, or a basic salt. A neutral salt is going to be one that comes from the reaction of a strong acid with a strong base. An acidic salt comes from the reaction of a weak base and a strong acid. A basic salt comes from the reaction of a strong base with a weak acid. So, two strong materials reacting, we get a neutral salt. If one is strong and one is weak, if it's the acid that's strong, it's going to be an acidic salt. If it's the base that's strong, it's going to be a basic salt. So we want to be able to look at salts and determine, are they likely to be acidic, basic, or neutral? And to determine that, we need to identify what we're going to call the parent acid or base. And that's going to be the acid and base that had to combine in order to form that salt. So what acid and base did we react in our neutralization reaction? Now in the salt that we form, the cation will always come from our base. So if we're trying to figure out what that parent base is, we take our metal cation and we're going to add hydroxide to it to determine the parent base. If the cation is nitrogen containing, then we're going to remove one of the hydrogens to determine the parent base. Now the anion in our salt will always come from our acid. To determine what our parent acid is, we're going to add a hydrogen to that formula. So we're going to take a look at a series of salts and we're going to determine if they are acidic, basic, or neutral. So first we've got sodium chloride. So we said that the cation always comes from our base. So to determine the parent base, we're going to take that metal cation, so that's Na+, and we're going to add hydroxide to it. So our parent base is sodium hydroxide. Our anion always comes from our acid. So to determine the parent acid, we're going to take that Cl- and we're going to add hydrogen to it. So the parent acid is HCl. So what we're saying here is that in order to form sodium chloride, we would react sodium hydroxide with hydrochloric acid. So sodium chloride is the result of that neutralization reaction. Now, if we look at these parents, I've got sodium hydroxide. So we want to identify are the parents strong or weak. So with my sodium hydroxide, that is a strong base. It's a group 1A hydroxide. Those are our strong bases. We look at our acid, HCl. HCl is in our list of 6 strong acids, so it is a strong acid. So the two parents, the parent base and the parent acid that form this salt, They are both strong. So we said that means we're going to generate a neutral salt. Now our next salt is a potassium acetate salt. So again, my cation, potassium, is coming from my base. To determine the parent base, we're going to take that potassium and we're going to attach hydroxide. So the parent base is potassium hydroxide. My anion comes from my acid. To determine the parent acid, we're going to attach a hydrogen. So this becomes HC2H3O2. So then we're looking at the strengths of those parents. Potassium is a group 1A cation, so this is a group 1A hydroxide, making this a strong base. The acid is acetic acid. Acetic acid is not one of my 6 strong acids. Remember, the 6 strong are HCl, HBr, HI, HNO3, H2SO4, and HClO4. And if an acid is not one of those 6 strong acids, then it is a weak acid. So my parent base is strong, my parent acid is weak. If it's the base that's strong, the salt is going to be basic. Now, right now, we're just focusing on identifying is our salt going to be acidic, basic, or neutral. But we'll talk in a little bit about why they are acidic, basic, or neutral. So looking at our final salt, we have NH4Cl. So again, the cation comes from my base. This time, it's not a metal cation. It's a nitrogen-containing ion. So we're going to take a hydrogen away. So NH4+, that is the conjugate acid of NH3. So NH3 is my parent base. My anion comes from my acid. We attach a hydrogen. So I have HCl. NH3 is a weak base. HCl is a strong acid. So this is going to result, when we react ammonia with hydrochloric acid, producing ammonium chloride. This is going to result in an acidic salt. So as I said, we're going to take a look now at why these salts would be acidic, basic, or neutral. So our pH depends on whether or not the salt ions have the ability to undergo hydrolysis. Hydrolysis is just the ability to react with water, to get proton transfer going with water. So remember that our strong acids have very weak conjugate bases. Those conjugate bases will not have the ability to accept hydrogen from water. That's why the reaction is not reversible and the acid is strong, because that base is too weak to take a hydrogen from the water molecule. So ions coming from strong acids will not undergo hydrolysis. Same is true for a base. Strong bases have very weak conjugate acids. In the case of a strong base, the conjugate acid is a metal ion. There is no hydrogen to donate, so there's not going to be any hydrolysis. So, so again, strong parents, strong acid, strong base. The ions they produce, the conjugates that form our salts, are too weak to take hydrogen from water, or they don't even have a hydrogen that they can donate. Now, if we have a weak acids have strong conjugate bases. That's what allows the reaction to be reversible, and we get more molecules of our original substance. Strong bases, or strong conjugate bases, will have the ability to accept hydrogen from water. Ions coming from weak acids undergo hydrolysis. Now, the conjugate base is going to react with water. It's going to take a hydrogen, and when it does so, we are producing hydroxide. So we're going to get a basic solution because that hydrolysis forms hydroxide. Now, weak bases have strong conjugate acids. And again, it's the conjugates that are forming our salt. So if the parent is a weak acid, it's releasing its conjugate base to form the salt. That conjugate base is going to produce hydroxide in solution. Weak bases have strong conjugate acids. Strong conjugate acids will have the ability to donate hydrogen to water. Ions coming from weak bases will undergo hydrolysis. And it's going to result in an acidic solution. So again, the weak base is producing a conjugate acid. That conjugate acid is going to donate a hydrogen to water, producing hydronium. So we're getting an acidic solution because we're forming hydronium. So we can take a look at a generic example. So I've got some acid, Ma. So I've got some salt, Ma. So I've got a metal cation and some anion. Now when that salt dissociates, we're going to produce the metal cation plus our anion. Now hydrolysis would be represented as follows. My metal cation, when we put it in with water, there's going to be no reaction if that metal cation comes from a strong base. If that metal cation comes from a weak base, it's going to look more like an MH+. That MH+ is going to donate a hydrogen to water, producing hydronium. Now my anion from my salt, that anion plus water is going to give no reaction if it comes from a strong acid. If it's coming from a weak acid, it's going to take a hydrogen from water, producing AH, so my original acid, and hydroxide. So we're going to go back to our first problem, and we're going to walk through looking at why each of those salts was acidic, basic, or neutral. So with A, we had sodium chloride. So if we dissociate our sodium chloride, it's going to break into Na plus and Cl-. So if we look at the sodium cation, we said that sodium cation came from sodium hydroxide. So it's coming from a strong base. Since it's coming from a strong base, it is a very weak acid. So Sb will be strong base, Wa will be weak acid. So since it is coming from a weak parent, it is not strong enough to interact with that water. There's no hydrogen for that Na plus to donate. It's too weak. So when we put it into water, we're going to get no reaction. My chloride, we put that chloride into water, we're also going to get no reaction. That's because that chloride is coming from a strong acid. That means this conjugate base is very weak. As a weak base, it's not going to have the ability to pull a hydrogen off of the water molecule. So it's going to remain Cl- and we get no reaction. So with this scenario here, there is no hydronium or hydroxide produced. So remember, our criteria for being neutral is that the hydronium and hydroxide are equal. So we put our acid in our base into solution, they react. The hydronium and hydroxide are reacting and producing water. We're not generating any additional hydronium or hydroxide, and so it remains neutral. So if we look at the salt we had for B, we had that potassium acetate. When that dissociates, we're going to get K plus and C2H3O2 minus. So looking at my cation, My cation, we said, came from potassium hydroxide. It's coming from a strong base. So that potassium cation itself, it's the conjugate acid of potassium hydroxide. It is a weak acid. It's too weak to interact with water, and therefore the potassium is going to generate no reaction. These ions that do not react with water, they are considered to be true spectator ions. So you might remember spectator ions from first semester chemistry. Remember, those were going to be things that were part of our original ionic compounds, but when the reaction occurred, they didn't change. And so in these cases, they're true spectators because they're not able to interact with water. They remain exactly as they are. Now, my acetate, this was the conjugate base of a weak acid. And therefore, it's not a strong base, but it's going to be strong enough to interact with water. And so conjugates coming from weak parents are going to undergo hydrolysis. So if this is a base, remember our bases are going to take a hydrogen from water. So we're going to get HC2H3O2 and hydroxide. So one ion gave no reaction, but the other ion is producing hydroxide. So it's increasing the amount of hydroxide in the solution, and therefore it's going to make it basic. So the potassium hydroxide salt is considered a basic salt because that acetate anion undergoes hydrolysis. It produces hydroxide in solution. Our final salt, we have our NH4Cl, which dissociates into NH4 plus and Cl minus. The NH4 plus, we said this was going to come from ammonia. So this is the conjugate acid of a weak base. Conjugates coming from weak parents react with water. So as an acid, that NH4 plus donates a hydrogen to water, reforming my original parent base and hydronium. My Cl minus, just like before with the sodium chloride, gives us no reaction with water. And so we are producing hydronium here. That makes us acidic. So ammonium chloride is going to be an acidic salt because that ammonium cation reacts with water, producing hydronium. So these are salts, but they're not going to have neutral pHs. So if I dissolved ammonium chloride into water and we measured its pH, we're going to get an acidic pH. Now, in each of these cases, we either had both ions not reacting with water, or at least one ion would react with water. We could encounter scenarios in which both ions undergo hydrolysis. And so in that scenario, whether or not a solution is acidic, basic, or neutral is going to depend on our K values. So we would have to compare the K of our cation to the K of our anion. If the Ka is greater than Kb, our salt will be acidic. If Kb is greater, the salt will be basic. And if they're equal, then we're going to generate the same amount of hydronium and hydroxide, and my salt will be neutral. So our next problem on our worksheet gives us some additional practice. So I would encourage you guys to work through those additional practice, and you can check your work on Blackboard.